Welcome back to Honors Calculus. In this video, we're going to be looking at the derivatives of sine and cosine, and then the other trigonometric functions. The theory behind differentiating trig functions is a little bit weird, so let's just dive right in. In order to work with limits on trigonometric functions, we're going to need a tool called the squeeze theorem, which makes a lot of sense, but the application of it is really strange. Given three functions, f, g, and h, such that f is less than g is less than h for every value, and that the limit as x approaches c of f of x is equal to the limit as x approaches c of h of x. We'll call that L just to have a name for it. Then it must be the case that the limit as x approaches c of g of x, the function in the middle, is exactly that L. We could use properties of limits to prove this. This is actually something that's not that difficult to prove using the epsilon delta definition of a limit, but I think that the visual proof is a lot more useful. So let's think about a couple of functions. Here I have f of x, g of x, and h of x. And here I have the point CL. If you ignore the line that I've drawn for g of x, the setup with f of x and h of x is given to us. We have these two functions that are doing their own thing, but at this one point, they converge and they meet at the same place. Then I've got another function that is somewhere in between them doing its own thing. The theorem tells us that the only way to get through the point C is to go through at exactly the same point that we had before. The function g of x, over here where the other two functions are spread apart, there's a lot of room for that to vary. There's a lot of different functions g that will satisfy. But as we come here, we get squeezed in. The distance between h of x and f of x becomes so small that the only way to get through is to go through that exact same point. That's what we mean by the squeeze theorem. That's the visual idea of what's going on. You can go through using an epsilon and delta definition. If you're interested, I have that typed up. I can send it to you. But I don't think that you gain anything by looking at that. So we'll leave it just with this. Because we need the squeeze theorem for exactly one limit. We need to use the squeeze theorem to show that the limit as x approaches 0 of sine of x divided by x is equal to 1. That is the only thing we are going to use the squeeze theorem for in this course. And to write this proof, I'm actually going to change variables. Because we're talking about an angle here, it's not unreasonable to, instead of thinking about sine x over x, to think about sine theta over theta. All right, let's pretend that this is a perfect circle. A sector of a circle is formed by taking an angle at the center of the circle and cutting it out. And when you find the area of a sector of a circle, we know that we can calculate the area as 1/2 of r squared times theta. That's a common formula in trigonometry. If I look specifically at the sector with radius 1, that means that the area of this thing is theta over 2. Now, when I'm thinking about a circle and an angle cut in the center of the circle, I start thinking a lot about trigonometry. I'm going to draw a nice big circle this time and hopefully do a better job than I did on the last one. Right. When I'm thinking about a circle, I can cut this wedge and use it as a way to form a triangle. I can form the triangle on the small side, and I can pretty easily form a triangle on the larger side as well. Let's not use blue. Let's use red here. All right, so I've got my smaller triangle that looks like that, and I've got my larger triangle that looks like that. I also know I have an angle of theta, I have a radius of 1. I've got a right angle here. So to find the area of these two triangles, for the shorter triangle, I need the perpendicular length. For the longer triangle, I will need, again, the perpendicular length. All right. So let's draw each of those two triangles separately. I've got a triangle here. I've cut down into it with a right triangle. I know that those two sides are both of length 1, and I need to know this perpendicular distance. Well, notice here that this is the side opposite the angle, and this is the hypotenuse of the angle. Opposite over hypotenuse is sine. So the height of this triangle is sine theta. The length of the base of the triangle is 1, and area is 1/2 base times height. So 1/2 sine theta. Then I'll go to my larger triangle. Once again, I know that this angle is theta, I know that this side is 1, and I know that I have a right angle. Well, the length 1 is the adjacent leg of the triangle, and the thing that I'm looking for is the opposite leg. Opposite divided by adjacent is tangent of theta. So the side I'm looking for divided by 1 is tangent of theta. And once again, the area is 1/2 times the base, which is 1, times the height, which is tangent of theta. Ordering these three triangles, or these three areas, we have an area that was formed by taking the sector and drawing a straight line, slivering some of it off. So 1/2 sine theta must be less than or equal to 1/2 theta. And then the tangent one was formed by putting an extra bit on. So that sector, 1/2 theta, has to be smaller than 1/2 tangent theta. All right, tangent is sine divided by cosine. And if we divide all three sides of this equation by sine of theta, I'll get that 1/2 is less than or equal to 1/2 theta divided by sine theta is less than or equal to 1/2 1 over cosine theta. Now, I also notice that I have a bunch of 1/2s. I might as well get rid of those at the same time. So 1 is less than or equal to theta over sine theta is less than or equal to 1 over cosine theta. Now I'm going to take a reciprocal. And when you take a reciprocal in an inequality, it changes the direction of the inequality. A really simple example of that, we know that 2 is less than or equal to 3, but 1/2 is greater than or equal to 1/3. So if I take the reciprocal of all three sides of this inequality, it will change the direction, and I'll get the reciprocal of 1 over cosine, which is cosine, is less than or equal to the reciprocal of theta over sine theta, which is sine theta over theta, is less than or equal to the reciprocal of 1, which is 1. And as theta goes to 0, we know that cosine of theta is going to go to 1. So we have here the squeeze theorem set up. Sine theta over theta, as theta goes to 0, has to be somewhere between 1 and 1. So by the squeeze theorem, ST, it must be that sine theta over theta is also going to go to 1. Now's a good time for a reminder. Our goal here is to find an expression or a way to differentiate sine and then later cosine. So that's what we're trying to do. We know that's what we're after, and we can try to head off in that direction. Right? This limit, the limit as x approaches 0 of sine x over x is equal to 1, is going to be one important feature. The other one should be something that you're already familiar with, namely the angle addition formulas. You should already know that if you need the sine of u plus v, that's going to be equal to the sine of u times the cosine of v plus the cosine of u times the sine of v. And there's a similar one for cosine, but it's not useful to us in what we're doing right now, but I'll mention it because it might be useful to you. The cosine of u plus v is equal to cosine u cosine v minus sine u sine v. All right, that's a thing that you should know from trigonometry. I'm not going to go through and prove that, but using that and using our limit that we got from the squeeze theorem, we should be able to figure out the derivative of sine of x. Well, by definition, that's the limit as delta x goes to 0 of f of x plus delta x. So in this case, that's going to be sine of x plus delta x minus f of x, in this case, just sine of x, all over delta x. And to hopefully no surprise, we have a sum of stuff inside of sine, so we're going to use the angle addition formula to rewrite that as sine x cosine delta x plus cosine x sine delta x. And we still have minus sine x, and the whole thing is still over delta x. All right, so notice that I have a couple of things here that have sine of x in them. Specifically, I have sine of x times cosine of delta x, and I have sine of x by itself, so just 1. I can rearrange that and then break apart my limits here. So I have separately sine of x. I can bring the factor of sine of x outside of the limit because it doesn't have a delta x in it. Right? We only care about things that have delta x. Things that don't have delta x are constant with respect to delta x, and can come right outside of the limit. So we're looking at the limit as delta x goes to 0 of cosine of delta x minus 1 all over delta x. And then we're looking at the limit as delta x goes to 0 of sine of delta x all over delta x. That second limit is the one that we just proved. That's equal to 1. The first limit we haven't looked at directly, but we can get there using the tools that we were just developing with that first limit. Right? And as I get here, I realized that I forgot to write down the next step when I was looking at those trig identities earlier. I said that cosine of u plus v is cosine u cosine v minus sine u sine v. The thing that I wanted to look at specifically was what happens if you have the same angle for both of these. So the cosine of 2u is cosine squared u minus sine squared u, which we can rearrange in any of several different ways to get something that is useful to us. Specifically, I like the version that uses the Pythagorean identity. Cosine is 1 minus sine. Which means that cosine of 2u minus 1 is equal to the negative of 2 times the sine squared of u. So if I let 2u be delta x, or u itself be 1/2 delta x, that means that I can rewrite this limit, the limit as delta x goes to 0 of cosine delta x minus 1 is the same thing as limit as delta x goes to 0 of minus 2 times sine squared of delta x all over delta x. And now I'm going to do something a little bit strange. I'm going to multiply and divide by delta x, so I can rewrite this as negative 2 delta x times sine squared of delta x divided by delta x squared. And the reason that I did that is that I can use the properties of products and quotients to split this up as the limit as delta x goes to 0 of negative 2 delta x, and the limit as delta x goes to 0 of sine delta x over delta x, the whole thing squared. And because this is finite and that goes to 0, I can come way back up here and say that this whole thing goes to 0. And so the only thing that's left is cosine of x. The derivative of sine of x is equal to cosine of x. The theory in this video is already getting fairly long, so I'm not going to go through and prove, but you can go through a similar idea using some trig identities and what we've already established to get that the derivative of cosine of x is the negative of sine of x. And then once you have that rule, the other trigonometric functions can follow pretty readily using some properties of derivatives that we'll be looking at as we go forward. But instead of looking at theory, I want you to take some time to combine these rules with the tools that we've already established and find the derivative of 2x minus 5 sine of x plus 7 cosine of x. Great. See what you can do with that one, and I'll see you in the next video.